this video, we're going to be going through quadratic sequences. Other videos and examples of them are going to follow. So here we're just introducing it. So say we have a sequence M, N, O, and P. Then it continues. And then we find the first difference and the second difference is common. So we can say that for the first difference, you know that you would say like t2 minus t1, which means it's n minus m. But let's say that n minus m is actually equal to x, and then o minus n will be equal to y, and then p minus o will be equal to z. Then we take what the second difference is. Then the second difference, we know that it's going to be equal. So we can say that the second difference is just a d. So we know that this is a second difference. And then this is a first difference. And then this is just a quadratic sequence. So I can say quadratic sequence. And then we see that the second difference is it's common. We say that the second difference is common because if here was 2 and this will be 2, but then the first difference is arithmetic, so it's an arithmetic sequence. Then I can just say it's AS. Then this one is just quadratic sequence. Next thing that we want to look at is what is a general formula or the general term. So we know that to find it, we say that 2a is equal to d, which is the second difference, and then we say that 3a plus b is equal to what the term over here for an arithmetic sequence, and then a plus b plus c is equal to the first term of the quadratic sequence. That is how you find your Tn. Then your Tn is equal to your an squared then plus bn plus c, whereby the value of c, it is this one, and then the value of b, there is the value of b, then the value of a, there is the value of a. So this is your general term. Then the next thing that we want to look at is finding the next term of the sequence. So we have seen what the general term of the sequence. So we have seen about the general term. So now we want to look at finding the next term of the sequence. Term or terms of the sequence. So say we wanted the next term, which will be the fifth term. Say we wanted t5. So t5, what you notice is that since we said that n minus m was equal to x, so that was the assumption that we made, and then we said that o minus n was equal to y. This means that n is equal to your m plus x. So what we want to look at, what? At slant, more like slant lines. Which are these lines that we drew? So the slant lines, they're going to give you the next term. So the sum of the slant lines will give you what? The next term, more like the sum of the slant terms. So we can just say slant terms instead. It is not what it's being called, but it is a simple way of looking at this. So if you say that m plus x, you'll get what the next term, because they are slant. Then m plus x, you can see that it's indeed equal to what? Equal to n, because if you shift this to the right hand side, you can see that it becomes n plus x. And you can see that if you say that O is same as what is y plus n, because if you shift n to the right, it becomes positive. But you can see that indeed that O plus n will give you O, because they are being slant. So every time when terms are looking like this on a quadratic sequence, when they add up, so if this is a quadratic sequence, so say it's another term, so this term, when you add it with this term is for what? Is for an arithmetic sequence, so as, which is the first difference of a quadratic sequence. And then if you add these terms, you will get the following term. So it is important when you are finding what the next term. The third thing is to notice that for every terms, maybe every n terms, so we can say for every n terms of a quadratic sequence, we have corresponding, we can say we have n minus 1 terms of an arithmetic sequence. As you can see it here, we have 1, 2, 3, 4 terms, but then for an arithmetic sequence, we have 1, 2, 3. So we will always have 3 terms of an arithmetic sequence for 4 terms of a quadratic sequence. So like it's more like they are always one less from a quadratic sequence. So if I give you a quadratic sequence and I tell you that we have 100 maybe in 55 terms, so this is a quadratic sequence. So you must immediately know that we have 154 terms for an arithmetic sequence. Why is that even useful? So say that I give you term number 124 of an arithmetic sequence, and I give you a term number 124 of a quadratic sequence. You must be able to see that we can find term number 125. So we can find term 125 of a quadratic sequence. Also, I want you to look at something interesting. See that term 1 for a quadratic sequence and term 1 of an arithmetic sequence, they are actually more like in diagonals. Term 2 is in diagonal to term 2. Term 3 is also in diagonal. So term 4 will be diagonal with this one. So what you want to see, or what we can say that is that term 4 for a quadratic sequence plus term 4 of an arithmetic sequence will give you term 5 of a quadratic sequence. So that is what we say. So you can see that term 4 of a quadratic sequence plus term 4 of an arithmetic sequence will give you term 5 of a quadratic sequence. So that is what we are saying down below. But what if we replace this as n and make up a general term for this? What if we just say Tn of a quadratic sequence plus Tn of an arithmetic sequence, since this was 4 and this was 4 and this is greater by 1, we can say Tn plus 1. of an arithmetic sequence. So we can just say Tn of a quadratic sequence, then plus Tn of an arithmetic sequence will give you Tn plus 1 of a quadratic sequence. Now we want to look at the parabolic qualities that the quadratic sequence shares with parabolas. So parabolic qualities. First, you saw that the general term was Tn equals to your an squared plus bn plus c, which is very similar to a parabola, which is y equals to your ax squared plus bx plus c. So we know that a parabola can look like this or can look like that. So this is often this is when your a is less than 0, and then this is when your a is greater than 0. So just like quadratic sequences, the same is going to apply. When a is greater than 0, we're going to see this, and then when a is less than 0, that's what we're going to see. But then how is it important? So sometimes we like to talk about the maximum and minimum term. The maximum and minimum term of the sequence. For example, you can have a sequence which is starting at, say you have a sequence negative 3, negative 2, negative 1, then 0, then it start being 1, 2, 3. Say it was continuing on this side and then continuing on that side. You can see that at 0, it turns around to be 1, 2, 3, and so on. So it could look like that, or it could look like that. Well, so this will depend much on the value of a for this sequence in order to see that does it look like this or does it look like that. So with that, you can see that this one has what, the maximum term. So it's more like the maximum value, and this one has the minimum value. And you can use parabola rules more like to find the terms. For example, you remember that in a parabola you have the axis of symmetry, which is x equals to your negative b over 2a. So it's more like here you have n equals to your negative b over 2a. So this is to find the value or the term at what? At a turning point. Term at a turning point. Remember, we're not like finding the value of it, but then we are finding that what term number is it? Is it term number 4, 5, 6, whatever that term is? And to find the value of it, we will have to take this n and substitute it to the original equation. It's more like when you are finding the y value for a turning point.